Hello, everyone, and welcome back. In today's episode, we are going to be continuing to explore this connection between the definite integral, also sometimes known just as an integral for short, and the graph of a function. Well, for the exercises that we will be exploring, first up we have the graph of this sort of piecewise linear function g of t. And we're asked, based on this graph, let's go ahead and try and calculate a couple of different definite integrals of this function. And first up, we have the integral from t equals 0 to an upper limit of t equals 2. Let's calculate that value of this function using the graph alone. Now I'm going to remind myself that the definite integral is equal to the net area between g of t and the t-axis. And in this particular problem, we are only caring about the interval of t's from 0 at the smallest to t at the highest, this lower t value and this upper t value, because those are our limits of integration. We are not to go beyond those limits. Now let's scroll back up to the picture and see if we can calculate, not estimate, but calculate this net area using the picture. So here is t equals 0, here is t equals 2, and the area that we are concerned about is the one that lives right here between the graph and the horizontal t-axis in this problem. Now my first question for you, is this area going to be assigned a positive value or a negative value? This would be assigned a negative value. Why? Because the graph is below the t-axis in this particular region. And since the graph is below the t-axis in this particular region, we communicate that by using a minus sign. So this area would be negative. Okay, this area would be negative. Precisely negative what? Because this particular region is triangular, I can actually calculate the area exactly, using a geometric formula. For a triangle, the formula is 1/2. Ooh, you can't see that yellow at all. Let's try again. It would be 1/2 times the base of the triangle, which is 2 units long, times the height of the triangle, which is 1 unit. And so this area would be -1 units, minus sign because it is below the x-axis. So this net area would be exactly equal to this definite integral. And so that would be my exact answer to this question, not estimate, but calculate the net area. The net area and the definite integral would both be exactly equal to -1. Same question, same function, different limits of integration. This time it's asking me what is going on between t equals -2 and t equals 0. So in this situation, the interval that I am concerned with is this one right here, going from t equals -2 to t equals 0. Once again, the definite integral is exactly equal to the value of the net area between this function and the t-axis. So if I can calculate the exact net area, then I will have calculated the exact definite integral. Now this region between -2 and 0 has a lot going on. There are for sure pieces of the graph that are below the t-axis. This region has the graph below the t-axis. This region has the graph below the t-axis. But this region in the center has the graph above the t-axis. Now notice that there is a quite beautiful symmetry. Just like in the previous episode, this idea of symmetry is coming back again. This triangle here in the middle, if I split it down the center, then this right half is an exact mirror copy of this little triangle piece down here. And this left half is an exact mirror copy and identical to this little piece down here on the bottom left. Now, because this upper piece is positive and this lower piece is negative, when I combine those in the total, they will cancel each other out. And the same thing is true over here on the right side. This positive area on this right side of the triangle and this negative area on this bottom part triangle, those when you combine them will cancel each other out as well. So in total, minus, plus, plus, minus all cancels out, and I get a net area of exactly 0, and therefore this definite integral would be exactly 0 as well. Same question, different interval. Calculate the integral from -2 to +2 for this function. Now, I think we can recycle some of our previous work in answering this question, because this question is asking about the net area all the way from -2 all the way to +2. But we've already calculated the net area on the left half of this picture. The net area on the left half is 0. And we've already calculated the net area on the right half of this picture. The net area on the right half of this picture is -1. So if someone says, I want the net area on the whole thing, all the way from the left side to the right side, then the area of the whole thing can just be found by putting the areas of the two halves together. And so I would say this is my answer to part 1. The area on the left half plus the area on the right half. In total, the net area would still be -1. So I want to pause here for a moment, because what we have just done in this moment is significant, and it's going to show up again in a later episode. What we have just said is that if you want the integral all the way from -2 to 2, you can basically take a pit stop at 0, find that net area, then continue from 0 onward, find that net area, and then just combine the two results. And those two net areas combined are equal to the total net area all the way from -2 to 2. And so symbolically, that sort of graphical, obvious reality could be captured in symbols by this. The integral from -2 to 2 of your function is the same thing as -2 to 0 plus 0 to 2. Finally, in the spirit of these exercises, same question, same function, but different limits. This time we are only going from -1 to -0.5. So the area that we are dealing with in that particular exercise is simply this one little piece of triangle right here from -1 on to -5. That area could still be found geometrically using the triangle geometry formula, where we have a base of half a unit, we have a height of 1 unit, and so this area would be equal to 1/4 of a unit, and this would be ascribed a positive value. Why? Because this region is above the x-axis. So the exact value of that net area is exactly equal to this definite integral, is exactly 1/4 of a unit. Alrighty. Now, in the same spirit of using graphs to calculate definite integrals, join me in this exercise. So with this exercise, they're saying calculate the value of this integral. The integral from 0 to 2 of the square root of 4 minus x squared. Now, later on in Calculus 2, you learn another way to calculate integrals like this one. A really bad way, a really slow way, a really terrible way that takes a lot of time and creates opportunities for many, many, many mistakes. And so what I'm going to show you is that this problem can be answered almost immediately, like in a couple of seconds, if you take the graphical approach to this problem and you answer this using the idea of net area. So reminding myself once again that the value of this integral is exactly the same as the net area between the graph of this function and the x-axis on the interval from 0 to 2, I'm going to get myself over to Desmos and I'm going to have a look at the graph of this function to see if anything stands out to me as interesting. So here is the graph in question. Here I am stretching from the domain of the graph is naturally -2 to 2, and I'm going to bear in mind that the only portion that I sort of really care about is this portion over here on the right-hand side, this portion from 0 to 2, because 0 to 2 are my limits of integration. Now the shape that has been formed by this graph is really unique and interesting. Do you know what shape is being formed here? If you can't see it, it may help you to see the reflection of this image on the other side of the x-axis. If I reflect this shape on the other side of the x-axis, you can see what is formed by that reflection is a perfect circle. And so what we have, if I remove the reflection, is a half circle. Okay, bearing in mind that the function that we're dealing with, when it is graphed, forms a perfect circle shape, let us see if we can use geometry to answer this question. Geometrically, we have a formula for the area of a circle of a given radius, right? Area of circle of radius, in our case 2, is pi times the radius squared, is 4 pi. Of course, this is the formula for the area of a full circle, and I certainly do not have a full circle in this problem. In fact, based on the information that we are provided, what portion of the circle do I have? Well, because the interval that we've been given to work with is the interval from 0 to 2, the only portion of the circle that counts is the portion on this right-hand side, starting at 0, going to 2, between the graph and the x-axis. So the area in question is the area of 1/4 of a circle, this quarter on the upper right side. Therefore, the net area that I am interested in calculating is the area of 1/4 of a full circle of radius 2. And so that would give me a circle with an area, a quarter circle with an area of exactly pi units. And we would have a positive area here because this region that we've drawn is above the x-axis. Now, because this is the value of the net area, and the net area is equal to the definite integral, that would be equal to the value of the definite integral as well. Now, let me just show you how, for example, an online solver would tackle this problem, so you can see what I mean when I say that this is really the best way to do it. So here is what we just did to answer this question. We said, oh shoot, that's net area. We popped out to Desmos. We looked, oh, it's a circle. I know the area of a circle. That's pi r squared. Cut that by 4. Answer is pi. You're done, right? Barely took up any space on the page at all. Now, if you try to answer this same question using an online solver, let me tell you what that looks like. So over here it's saying apply trigonometric substitution. What the heck is that? Then it turns that integral into a different integral, and they had to use a trig identity and then they had to use another property, and then they had to integrate that and plug things back in, simplify, and here we are. Finally, they got their equals pi at the end of all of these steps. And honest to goodness, compared to what a student would write down, they're not showing a lot of their work here. So a student would trying to use this method to solve this problem, it would be even more work for them. It would probably be at least a full page of written work. So, as you guys are doing your exams, as you guys are doing your homework, I don't want to see y'all solving this problem this way. That's silly. Don't waste your time. Just use the graph. Just use the graph to answer the question. It'll take all of about 5 seconds once you get used to it. Use the graph, it'll save you a bunch of time. Now, let's remix this a little bit, add a little bit of extra flavor. Someone says calculate the value of the integral. Now we're going from -2 to 2 of x times that square root quantity, 4 minus x squared. Again, I'm going to go to the graph of this function, and I'm going to see if I notice anything interesting about this function. Okay, here is the graph of the function x times the square root of 4 minus x squared, going from -2 to +2. Do you notice anything interesting that might inform this integral calculation? Well, once again, if we think about this as a net area, there's a symmetry here. This portion on the right side of the picture and this portion on the left side of the picture are mirror images of each other. They're exactly the same. The only difference is that this guy over here on the right side is positive because it's above the x-axis, and on the left side it's negative because it's below the x-axis. If I combine those two areas, they're going to cancel out. So in total, I can answer this question again very, very, very quickly just looking at the graph. I could say 0 due to symmetry. Now finally, there may be situations where your graph is not suitable to find an exact calculation for the net area using geometry. However, it is always possible. It is always possible to use net area to estimate and approximate the value of your definite integral. So here, for example, we're given the graph of some function f of x here below, and they're saying use that graph to estimate what would be a reasonable value for the integral of this function from 0 to 2. This is really useful, once again, for checking your answers, for checking your work. If the value that you get from your definite integral is vastly different from the net area that you estimate from the picture, that's a sure sign that your calculations are probably wrong. So remembering that this definite integral is equal to the net area, I'm going to try and eyeball and estimate the net area. Maybe I cannot use geometry, but I can always estimate area simply by counting squares. So I can see that between x equals 0 and x equals 2 in this picture, I have several full squares. Looks like at least 4 full squares here. A little bit shaved off, but close to 4. 4 full squares. These two together look like they could be about half a square more, so we're up to roughly speaking 5. This one and this one looks like it could make maybe about 6 squares together. And then we have a tiny portion here and a tiny portion here of a square. So I'm thinking somewhere around 6.5 full squares. Thinking somewhere in the ballpark of 6.5 squares beneath the function and the x-axis between 0 and 2. And so 0.4 squares each of area 1 gives me a net area of approximately 0.4. I can just eyeball that by counting the squares that are under the graph and the portions of squares. So this means that if you integrate this function from 0 to 2 and you get a value like -10. You get a value like 35. You get a value like 114. That is silly. That cannot be correct. The answer to this question should be somewhere in the ballpark of 6 or 7 units. Not that far away from 6 or 7. Somewhere close to that, but definitely not 100. You understand what I'm saying? Definitely not 100 makes sense as an answer to a question like this one. Okay, so that concludes today's video. The point of today's video is that sometimes when you have geometry, when you have symmetry that you can use, graphs can be used to very, very quickly and efficiently determine the value, the exact value of a definite integral. Even if you cannot use symmetry, even if you cannot use geometry to find the net area exactly, graphs can always be used in all cases to estimate the value of a definite integral.